Okay, this morning is on fast Poisson solvers. You've seen that you can never get away in fluid mechanics from solving a Poisson problem, and there are, for an n by n grid, we have an n squared by n squared matrix. Direct inversion would give you an n to the 6 operations. However, the matrix is sparse, and in sparse matrices we iterate down, and in Gauss-Seidel we'd only need n squared iterations, which would reduce the size of the problem to n to the 4th. Successive over-relaxation gets it down to n cubed, and the first one I'm going to describe now will get it down to n squared. So there are faster methods of solving the Poisson problem. They're more complicated. That's why I rather like successive over-relaxation. It's not very complicated. These other ones are much more work to code up. So we're having 4 of them. Multigrid, really just a remark that we've done fast Fourier transforms. Not going into any details. Another one is domain composition. And for interactions between particles, like stars in a galaxy, where you've got a long-range 1 upon r squared force interaction, there's a thing called fast multipoles. Okay, so 4 little methods. The multigrid. So here, this first remark is exactly what I've said. We can get the number of operations down from some large number of n to the 6th to n squared. What's the problem with Gauss-Seidel is, why do we have to have n squared operations? Because the relaxation process is rather like a diffusion process, and we've got to diffuse all the way across the grid. Our errors have got to diffuse across, and if it's n distance away, diffusion processes take a time length squared, so it's n squared iterations are required. So the finer the grid, the more iterations, the further it is away you've got to diffuse. So the idea in multigrid is there are long wavelength errors that we've got to handle. Why don't we deal with them on a very coarse grid where things will diffuse fast? And then once we've dealt with the long wave errors, we can drop down to a finer grid with shorter errors, and we can then not need so many iterations because we only have to diffuse half the way across the grid. And multigrid takes that idea to the limit and says, we'll have a whole hierarchy of grids. We'll start with the finest one that we want, and then we'll coarsen it, and then we'll coarsen it, and we'll coarsen it, and we end up with the coarsest grid, which is just 1 point unknown in. The grid block is half the interval. Okay? So it's all about how do you transfer from the fine down to the coarse, and having got this solution on the coarse, how do you go back up to the fine? And that's called a V cycle. You go down from the finest to the coarsest, and then go up from the coarsest to the fine. And the trick is to worry about the residue. So you have an approximate answer. So we're very much tackling AX is equal to B, and we have an approximation. So we define the residue. And we hand down, the idea is to get the residue to get smaller and smaller, and we hand across from one grid to another grid the residue. It's an idea to know what I'm trying to do in the detail, and the detail will be a bit too complicated perhaps. Okay, so we have effectively a sequence of Poisson problems. There are various levels from k equals m at the finest grid to down to k equals 1, where there's just the coarsest grid, there's just one unknown in the middle because the step sizes are half. I probably skipped over here. It says that the coarsest has delta x is a half, and then there's a sequence going down to 1 upon half to the m. So we need the finest one to be a 2 to the power m. So n, the number of points on the finest grid has to be 2 to a power, so we can have this nested sequence. One is twice the other, one is half the other. Okay, there are these V cycles where we start at the finest, go down to the coarsest, and then go up. And we start the very first on the finest with a null solution. We say this is 0, and then we do a couple of iterations. So this is complicated. You start with K, the level of interest, as being the finest, but suppose we're at some level K going down to the coarsest. You have this question, so you iterate the Gauss-Seidel, which ought to take lots of time. You just do 2 iterations. Hardly any. Very crude. And then you get some approximate answer, not a very good answer, and you form the residue, which is the forcing minus your approximate, current approximate, and you go and store that residue. We'll need it later. And then you have to do some coarsening. So you have a coarse grid that we're going to, and then we have a finer grid that's nested with this. And we send the data, so we have some data there because these are. So to find out, we're going to coarsen the residue to form the forcing for the next level, for the coarser level. And we take a quarter of that, we push that side, this information that we have from this point to there, we take this information, and this information with a weight, whatever it says, an 1/8, and then there's some information over here, and we push that across, this across, this across, this across, and we, with a weight of a 16. So we average from the finer grid onto the coarser grid with assorted weightings, which is what this matrix is telling you, is you take a quarter, an 1/8, and then a 16th. So we coarsen the residue to form a new forcing at the next coarsest level, and we store that because we want to use that later. And then you zero the x that we're going to solve, ready to go, and then reduce k from this to go to a coarser level. And then you think, is k bigger than 1? Am I not at if I'm not at the very coarsest, go back to the top. That's true. And you keep going down, round, reducing k every time as we get into coarser and coarser grid, until we get to k equals 1. At k equals 1, we have just step size of a half. There's one unknown in the middle. Gauss-Seidel will solve that exactly in one go. There's only one variable. Okay, so we've solved exactly the coarsest one, and then we have to go back up to the finest one. So going up, we've dealt with k equals 1, exactly. So we would be starting at k equals 2. And suppose at some stage you are at a k, level k. What you have is the previous coarse solution. So we have the solution on the coarse grid. And we've now got to find it on the fine grid. Well, for this point, which is both on the fine and the coarse, it's pretty obvious. You just take the value. For the fine point, which is in between two coarse points, you take the average between the two. Then there's another point on the fine grid, which is not on one of the coordinates, and then you take an average of the 4 points around it. Okay, so it's linear interpolation of your coarse data onto the fine data. And that's what this matrix is all about, is that interpolation. Okay, so this produces, so we take this coarser solution and we call it a correction, and we add the correction to the stored approximation from that level. So when we went down, I said, please store the approximate solution. We store that. We've been tackling residues, so bits from the residues are additional bits that will correct solutions. So we have this approximate from going down, the V, and then we have this correction which we add to it, which gets us a better approximation. And then we take this better approximation and do a couple of Gauss-Seidel iterations. Only 2 is enough. So we get an even better solution. So now we've got an even better one. We then go to a finer grid. And there's a question, are we at the finest? If not, go back to the top. And if we're at the bottom, we've completed a cycle. And typically you would do 3 cycles, for reasons I'll explain. So here's my test problem. You know my problem off by heart by now. Del squared phi equals sine x sine y. Where I've applied this to, and my finest grid is 256 by 256, because it has to be a multiple of a power of 2. And there are various curves. This is the residue when you end up at the top of the V. This is the residue which starts before, when you first start, the residue is actually 10 before you've done anything. And the residue goes down with the number of cycles, but I'm multiplying the number of cycles by the number of Gauss-Seidel iterations I do. So I said 2. So it turns out if I do 4 Gauss-Seidel iterations, I need half the number of V cycles. And the very nice feature is, on this test problem, which I think is typical, is that 1 V cycle, the residue reduces by 10. Right. Now it turns out in this problem, the residue is about 10 times the error in the solution. Sometimes the residue is 1/10 of the solution, or even smaller. But I happen to know, by a little bit of theory, that for this problem, the error in my solution for psi is 1/10 of the residue. So if you want me to have 10 to the -4 accuracy, I need only do 3 V cycles. The cost of a V cycle is 8n squared. A cost of a V cycle with 2 Gaussian iterations. So obviously on the finest one, I'm doing n squared points, so I've got an n squared issue. The interesting thing is when you go to 1 level coarser, you've got a quarter of the number of points. So I've got quarter n all squared. And I go to another one, I get a 16th of n squared. And the sum of all those is just changes you from 3n squared to 4n squared operations. So these very coarse grids hardly cost you any work. But it's a fantastic method of spreading these long wavelength errors. I'm very enthusiastic about this method. It only works on a square grid. Okay, you can make it slightly better. Yes. So at the finest level, a Gauss-Seidel iteration costs you n squared. I said do 2 Gauss-Seidel iterations, which is 2n squared. I have to do this is say going down. I have to do an interpolation or a coarsening. That's an n squared operation. So it's 3n squared operations at the finest level to do one thing. And then at the next, but I have to come down and go up, which means 6n squared. But then the sum of 6n squared times 1 plus a quarter squared, a 16th, plus a 32nd, plus, blah, 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 plus, gets me from 6n squared to 8n squared. Okay. Method 1, any questions? Ready? Method 2, fast Fourier transforms. So this is possible only if you've got a square geometry, really, and you can use Fourier series, discrete Fourier transforms, and for which there is a fast inverse. Remember the fast inverse, instead of being an n squared operation, it was an n log n operation. So there's, you can, the simple-minded in 2 dimensions, if you have an n by n grid, you've got n squared coefficients, and each is the sum of n squared points, so it looks like it's an n to the 4th activity. There's this clever trick of the Orszag speed up, where you realize in this double sum you keep on repeating things, so if you don't do that, you can drop it down to n cubed, and then those sums, if you split the odd ones and the even ones, and then the odd ones and the odd even ones, etc., the fast Fourier transform technique, you can knock that down to n squared log n. And that's good. So that's right. Method 3. Method 4 is the hard one. It's domain decomposition. And it really is used, I'm going to think about it in terms of finite differences, but with a little ingenuity, it is used for finite element, and is used in a very big way. So if you want to do flow past an aircraft with wings and engines hanging off and things like this, this is really complex geometry. You're into finite elements, and it's a very big domain that you're involved in. And domain decomposition is you chop the big domain into little bits, and you work on each little bit on its own, parallel processing. So that means enormous speed up if you've got multiple processors. And the other big benefit is a big problem won't fit into a computer memory. But if you chop it into bits, each bit will fit into a computer memory. So you get a big saving in storage as well as a speed up. And the speed up works like this. Suppose we were to do direct inversion on an m by, and we had a matrix m by m. The cost of an m by m matrix, to invert it by a direct means, would be m cubed. Suppose we chopped this into k subdomains. Then we'd have m upon k by m upon k matrices. We have k of these matrices, but the cost of inverting the subdomain matrices is that, and then multiply by the number of subdomains, the total work's gone down. Particularly if we can do, it's even better as getting a result in half an hour's time, if we can parallel process these separate domains. Okay. It's hideous to program. One of these things you shouldn't do. Okay, so the method is divide the domain into many subdomains. For each subdomain, you have to identify the points that are inside and the points on the boundary. So a test for a point in the interior is that it only wants to know about variables which are on the interior. A point on the boundary will want to know about variables in this subdomain and variables in the adjacent subdomain. So we have boundary points. Sometimes the boundary points are 2 or 3 wide, depending on the type of differential equation involved. But we have boundary points, and then we have internal points there, and these internal points don't talk to these internal points. They only talk to themselves and the boundary points. So we have boundary variables y, which are global. There are boundaries throughout the system. And there are internal variables, and there's one set of internal variables for each subdomain. So what we do is we solve the subdomain problems. We find out the variables into the subdomains in terms of the boundary domains, and then we go to the boundary problem, which is called the Schur complement, and we solve just the boundary problem. So to this, I have to add a term which is global and is the number of boundary variables cubed. Okay. So for the Poisson problem, Ax equals b, if you divide it into k domains, we're going to get k, so these are vectors of variables. We get variables for subdomain 1, subdomain 2, up to subdomain k, and we get some boundary variables. So the matrix, the problem for Ax equals b, turns out within a subdomain to be the subdomains A times the applied to the k subdomain, and then we pull in some boundary variables is equal to the forcing in the subdomain. And the problem for the boundary problem will be another set of matrices acting on all of the internal variables, and the boundary variables is equal to some forcing. So I've turned the matrix A into a block. There are zeros where you don't see anything, and so there's just diagonal A's working on there, coupling to the y variables. So I can go away and solve this equation that the internal variables are equal to b minus by and then A inverse. I might do the A inverse by direct solving if the subdomains are small enough. I might do it by an iterative process if the subdomains are big. And then I can substitute the solutions. Having found the subdomain ones, I can substitute into this to get an equation for the boundary variables only is equal to the forcing. Okay, so this is a more refined version. In 2 dimensions, if we had an n by n grid, it is n to the 6 cost. If we divide them into subdomains, it would be n squared divided by k all cubed. And then the boundary size is likely to be n times the square root of k. The more subdomains, the bigger I have. And I have that cubed. And this is saying if you divide 100 by 100 grid, divide each direction by 5, so we just have little 5 by 5, so sorry, 20s. We have 20 by 20s, 5 of them to get to 100. Then the full cost is 10 to the 12, but with domain decomposition, it can drop down to 10 to the 9. However, this 10 to the 9, we can do quite a lot of parallel processing. And it may be a good idea to divide this domain into smaller bits. And in 3 dimensions, there's an example where if I divide, I'm dividing the 1 to 100 just 3 times, I can change from 10 to the 18 down to 10 to the 14. It is this idea underneath that the problem is not as big as you thought it is, because if I break it up, I can actually reduce the size of the problem, plus the advantage of parallelization. Okay, the fast multiples are a different sort of Poisson problem that occurs when you have point particles. So I might have point particles in Stokes flow. I might have, very much in colloids, I'm interested in that, in my own world. But on a much grander world, the people who do the dynamics of stars that make up a galaxy and show how 2 galaxies collide with one another are interested in the gravitational forces between all the stars. And they don't have the real number of stars, but they still have hundreds of thousands of stars to make a galaxy. And they're doing long-range interactions, 1 upon r squared interactions between these very many things. And because every long range means that every particle interacts with every other particle, if you've got m particles, it looks like there's an n squared calculation. And by clever techniques, we can reduce, in the first one, we can reduce n squared to n log n, and then amazingly, by the second clever one, you can actually reduce the n squared interaction into just n. Unfortunately, there's an enormous coefficient. So it only becomes useful if you've got over 1 million particles. Okay, the simplest one, called the Barnes-Hutt algorithm, is to think when you've got lots of things interacting, if I'm interested in what's acting on here, and there's lots of things over there, I cluster those together and replace all those individuals by an effective particle out there. So in gravitational terms, what's the total mass out there? And I just do a simple interaction between the total mass there with this point here. The second, more sophisticated one is to say, well, all of these particles here are not quite just a pole. There's a bit of a dipole, a bit of a quadrupole, a bit of an octupole. So I represent this cluster by pole, dipole, quadrupole, etc. And then I do that far-field interaction with this one here, plus another trick. Okay, so let's start with the notation I'm using here is that I've got sources. I'm using complex variable notation to tackle two-dimensional worlds, and I'm looking at just the potential, which is log r, but I'm doing it with complex variables. Actually, the complicated algebra later on is simpler if I do this complicated thing here. Okay, so the potential I'm trying to find at some particle will be the sum over all the other particles, J, summing over all the other particles of the pole strength, Q, the source strength of the other particles, times log of the distance between them. So that's the interaction, which looks like an n squared calculation if I calculate W at each of the endpoints. Right, before we get going, we have to talk about trees, roots, and leaves. We do a hierarchical system, rather like the multigrid, where we start with the big box that we're doing the calculation in, and then we divide it in 2 dimensions into 4 cells. And then those 4 cells we each divide into 4, and then those subcells we each divide into 4, and we go down log n levels. So we end up with n little boxes at the finest level. And that means, on average, there's only one particle in the finest little boxes. Of course, many of the boxes are empty, and a number of the boxes have 2 or 3 particles in them. But we just go down to this level where there are n boxes. Halfway down this hierarchy, you've got a box. The finer boxes, the 4 little sub-boxes inside your box are called children. And the 4, you're in a box, and you're one of 4 in a bigger box, and that's called your parent. And then you go up parent, parent, parent. The top is called the root, where you start. And you go down these branches until you get to the smallest box, which contains one or more particles, which might not be the smallest possible box, but the smallest end, the smallest box down that branch route that only contains one or more particle is called a leaf. Okay, there's some words. So, rather like multigrid, there's an upwards and a downwards path. So you start at the finest level. You don't deal with the boxes that don't have anything in, so you start with the leaves. And you start with the smallest leaves, the leaves with the smallest boxes. And you may have one or two particles in there, and you sum the charges, the source strengths of all the particles inside your little box. And more than that, you find out the center of mass. There are different positions in this little box. You find the center of mass. So you're going to replace those several little sources inside the box by a single particle of the total source strength at the center of mass. And you do that at the finest level, then you go up a level, you may gather a few more leaves at this. So as you go up, you will get these, you will have a box which now only contains, if it has leaves underneath, it will only have one particle at the center of mass, one effective particle at the center of mass, but you will have now 4 of these effective particles with their different center of mass, and you add the 4 together to get a grander particle at its grander center of mass. And then you go up a level, etc. Right? So that's collecting the clusters. And then on the downward pass, you start with 4 boxes, and if you're thinking of, okay, for the Barnes hut, you pick a particle, and you have to go through all m particles. So you pick a particle, and you start with big boxes, and if a big box is far from this particle, then you sum the cluster effect. You take for that big box over there, you take the effective particle strength at its center of mass and calculate the interaction with this point of interest. And then you go down to a finer level and you collect more far boxes. And then you end up at the finest level where the adjacent boxes are not far, so you have to sum the individual particles in the nearby ones. So what do I mean by far? I mean that a box isn't adjacent to this box. The particle of interest is in a box, and a far box isn't touching that, isn't adjacent to it. It has to be remote. Okay? Once it's that far away, we can deal with all the particles within it as an effective particle. Okay. So that's what it's saying here. And that process ends up being 27 n log n, and that means it's beating n squared, the direct summation, only if you have 200 particles, which is not many. In 3 dimensions, it seems to me to be 189 n log n, and that's only better than n squared when you've got 2,000 particles. So, yeah, you would not contemplate a calculation with less than 2,000, so it's worth it. That's just treating the clusters as poles. So we now get to fast multipoles, and they have a number of clever tricks. So firstly, if you have a source at a particle I, you replace it by a source at the center of the box at C, x, z, c. So it's a source there, but plus multipoles there. So we've got here 1 upon the distance from the center, some power, and then some powers here. I think that's correct. And I need an R here. So the dipole is z minus z squared. The quadrupole is z minus z cubed. However, because we start with the sources, poles. However, when we go some level down, we have some higher poles, dipoles and quadrupoles, depending on the index m, centered at the center of a box, where we're going to collect these different children boxes to the parent box center. And so we have to transfer this higher order pole to higher order poles around z equals zc. So we have obviously r equals 0. That means this has got the power m, but then there are some higher poles that are introduced by this transferring the origin from Zi to Zc. These are binomial coefficients. So that's the way we collect up the initial poles into being poles and multipoles about the center of a box, and then we collect these boxes into a bigger box to get poles and multipoles around the center of that box, etc., etc. Right. So we've collected all these up, going from the finest down to the coarsest. Now we've got to go back up, and so we start at the root, and on the way up we have a parent, and there's something called a fast shift. So at some stage inside a parent we have a power law, a constant, a linear, quadratic variation of the field from everyone else inside our parent box, and we have to transfer it from the center of the parent to the center of the child. And there's a way of changing this z minus zp to a power m to being z minus zc's, the various powers, with some binomial coefficients. And then we might have a pole, and we'd like to transfer a multipole, that's a 1 upon z minus zb to some power, to being around the center of the child. And that's done that way. So we have these local shifts, local expansions, and then in the downward pass, the box inherits from its parent. The parent thought it had a constant, a linear quadratic variation within it, which is equally true of the children within it. They have exactly the same linear thing, except it has to be re-expressed about the center of the child. And then we pick up some new ones from the 27 boxes around us, which are far, which weren't far for the parent. So new far boxes. So these are adjacent boxes to the parent, but now they've become remote far boxes, not adjacent to the child. And we keep going down like that, and when we get to the lowest level, we do exactly this, and then we have to add the direct interactions from our own box and the 8 boxes around us. So this is in 2 dimensions. The problem is, in 3 dimensions, there's rather a lot of new adjacent, new far boxes. Okay, so you have to work out about errors. What is the error in this method, where we're replacing the cluster here by something at its center and some multipoles, and you get the biggest thing by getting as close as you can to that multipole, which is a whole box separation apart. And then the first multipole you didn't include, that would be a power of the largest power that you included plus 1. And this is the closest that you can get to a particle which was there, which has been shifted to the center, and it shouldn't have been. And you can decide if you wanted 10 to the minus 3 accuracy, you have to have level 6 multipoles in 2 dimension, or you need 8 levels of multipole. I don't know what is. We're up to 256? So it's a 256 ant pole. Okay, so the costs are very much of this fast multipole are order n, but they have these coefficients. And in 3 dimensions, those coefficients are a bit bigger. And as it says here, if you want 10 to the minus 3 accuracy by including 6 levels of multipole in 2 dimensions, you need at least 10,000 particles before it's worth it. And in 3 dimensions, if you want 3-figure accuracy, you need more than £1 million before this is worth it. plus the fact it'll take you a week to code. Right. So there are these clever things. A number of people have tried to flog you multipoles, and I wouldn't touch it, really, because it's just very complicated to code, and you need such an enormous number of particles. So it's a very clever idea that you can change an n² problem to an n problem, but it's a big number times n. And if you wanted more accuracy than 10 to the minus 3, you really have problems. Okay. The difficulty in 3 dimensions is that the dipole can be in one of 3 directions. And the number of quadrupoles there are, I have no idea. Well, it's p to the upper m lower 2. Is it any good for, it's a nice question, could we use any of these multipoles for interactions between atoms, molecular interactions between atoms? And the answer is there's no need, because the interactions between atoms are not long range. So there is agreed electrostatic interaction, but atoms are neutral. So at worst they're right. So if you wanted to have a very simple atom with a two atom, very simple molecule, which has just a couple of atoms, nuclei, and you want to do the interactions between the electrons, then of course interactions between electrons are charge interactions, and therefore 1 upon r as far as potential is concerned. So it's a long range interaction, so you could do this. But there aren't atoms with 1 million electrons. And when you get to several atoms, it's electrically neutral. Electrostatic forces are so strong that it's very difficult to build up much free charge. And then the other reason you can't do it for atoms is they're quantum mechanical. The electron cloud is a quantum description, isn't really necessary. Yes, I've done the shift in 2D, because the shift in 3D, well, it is, okay. So the multiple, so you have a fundamental solution, a monopole, which is 1 upon r, and then the dipole is best thought about as the gradient of 1 upon r, and the dipole is gradient of 1 upon r, and if you can handle it like that. And then the shift, so you've got a source here, but you'd really like to express this source as a source of multipoles around the center of the box. So you just do a Taylor series of 1 upon r about this point here, which will generate a 1 upon r about here, but plus all the gradient terms, which you have to chop at some stage. Yes, almost certainly in 3 dimensions, you don't want to think about Legendre functions as the harmonics. You want to think about gradients. There's a little redundancy in the gradients because at the second order, in gradient of 1 upon r, you know that del squared is equal to 0. So not all gradients are totally independent, but you want to live with that. Okay.